Hello everyone, my name is Simon. I've just finished my first year as being a math student, and when I looked back on my notes and lecture scans given by my professors, I feel like I can understand more content on the lecture note, and there are more series which I could convince myself they are literally true by some kinds of procedures. And so now I would like to what share my thoughts with more people in the form of this kind of videos. And I do indeed hope that this could be a motivation or a navigation to those who interested in mathematics, especially interested in the near future undertake a math undergraduate level degree. And if it really does this job, I'm quite honored for the fact. Okay, that's for the introduction. So let's get on to the main topic for this video. I would like to start with Taylor theorem. So Taylor theorem, what it basically tells us is that if you are trying to find out an approximation to a particular kind of function, then the following formula acted as a remedy. It should be listed out on A-levels books, but I don't remember the detailed information on whether no, sorry, the detailed information on why this theorem holds in this way is not written out in full on a book. So here are the procedures which may convince you that it is indeed true in this way. Let us just review a basic tool. What we have got is that when you are trying to do an integral, say in this example, we want to find out the integral of a function f to the n plus 1's derivative from the interval 0 to x. The result turns out to be f to the nth derivative of x minus f to the nth derivative of 0. In this case, f to the n y is the primitive function, and to conduct the integral, we can then rearrange the above formula, and then we can know what is f to the nth derivative of x. What does it look like? Particularly if we take a specified value of n, in this case n be 0, we can find out an approximation of fx on a given condition. We would like to get closer to what we are trying to explain and explore. So we conduct the following procedure: let y equal to x times z1, where z1 is a variable and x is a constant. In this case, dy is equal to x times dz1. And as you can see in this row, if we do this kind of y substitution, we have successfully taken out x as a constant, and that means we are moving a step forward towards our target. And if we just conduct this kind of procedure, similar procedures repeatedly up to a certain level we would like to get, it should be obvious to find out the result we want. But just pay attention with the calculation. As the levels goes up, the second derivative, the third derivative, the calculations will be more complex, more and more complex, and it's quite easy to make mistakes. Actually, in this page, the calculation, in this page and the next page, I have made some mistakes before I finally found the road to success. So just be careful with the calculations at all time. Sometimes this do really means a lot. You can see that I've proceeded the first 4 terms of the whole series up to the x to the third power over 3 factorial times f to the third derivative takes value at 0. Why I do that is that from this term and onwards, we can find out the pattern of the series. Just judging from the denominator, it is indeed following a pattern of factorials rather than a arithmetic sequence. It's quite clear. Okay, that's all for the explanation. After we have explored by ourselves, we can just use the result we found full of joy and apply this result to find approximations to several other useful functions. Here are some examples, like Euler to the x power, and trigonometry functions like sine x and cosine x. Here I will just say a little bit more on sine x. You can see that when x is equal to 0, sine x is also equal to 0. So the first term, f0, vanishes. And the second term, x times f to the first derivative, 0. Since sine x, you take the first derivative, it becomes cosine x. Cosine x, when x is equal to 0, cosine x is equal to 1. So the first term of sine x is just equal to x. And again, cosine x derivative go backwards, takes the value at 0, is 0 itself. So again, x squared over 2 factorial vanishes, and the sequence jumps to x to the third power over 3 factorial, and so on and so forth. Exactly the same procedure goes to cosine x, except the starting point changes to f0 is the first term of cosine x. Alongside the trigonometry functions, there is another kind of functions, namely x is equal to cosine alpha and y is equal to sine alpha. These are just points on the right-hand branch of hyperbola x squared minus y squared is equal to 1, and it is called hyperbolic functions. Basically, there is not sign changes when they are differentiated to each other. Cosine alpha differentiate to sine alpha and vice versa. And so we can figure out the main difference between sine x and sine x, their approximations, is that sine x, there is a alternate sign change, plus minus, and so on. Whereas sine x, all the terms are positive, no negative terms. And Next is another problem. Since all these functions are expressed as the form of infinite sums, um, we might have a doubt whether these infinite sums become infinite ultimately. And we have a criteria to check that. To prove that, for example, y is equal to e to the x will convert to a finite value, given that it is a sum of infinite sums with a criteria. The limit n to the infinity absolute value of an plus 1 over an, where an is a general term of the sequence, is less than 1. Here I would like to, by the way, say a little bit on what do we mean by a limit. Just say a little bit. I should take an example of sequences. Basically, the definition is like that. If there exists a n0 or something else for all n greater or equal to n0, the absolute value of Sm minus L is less than epsilon for all epsilon greater than 0. If the above condition has been satisfied, L is called the limit of sequence. Here's the definition for limit of sequence. And then we go back to derive of the criteria. Oh. We can substitute an as bn times x to the n, and which is called a power series because it involves powers. And we just substitute this into the original criteria, and we can get a radius of convergent, the terminology referring to the limit n to the 0 of the absolute value of bn over bn plus 1. And then we can apply this to check our, for example, e to the x, this power series. And finally, we have found that the radius of convergence in this case is infinity. And so no terms will go beyond than infinity. And then we can judge that e to the x is indeed convergent. And so we can feel comfortable about this result and with no doubt on it. Oh. And here we come for a last point, some standard limit results. The first one can be understand quite easily just from the power series we have got in the previous pages. The limit when x to the 10 to 0 sine x over x, what is it equal to? We just plug the formula of sine x, and we found the first term is 1, and all the other terms is some form of x to the nth power where n is greater than 1. And just think a little bit on it. When x is 10 to 0, all the other terms, x squared, x fourth, and so on and so forth, they should be 10 to 0 in a faster pace than x itself. So undoubtedly, when x is 10 to 0, all these terms will 10 to 0 as well. So combining together, the ultimate result for this limit is indeed 1. And in other cases, if we do an equivalent substitution, let y equals to 1 over x, we can find out when y tends to infinity, limit y times sine 1 over y is equal to 1. And the final limit I would like to talk about is tangent x over x when x is 10 to 0. We can see that it is equal to sine x over x times 1 over cosine x. Cosine x, when x is equal to 0, cosine x is equal to 1. And sine x over x is a limit we have just found out. So the result is also quite clear. Then that is 1. I shall stop here for this video. And for the next video, I consider to talk a little bit on some other usages directly or indirectly of this power series. For example, Euler's formula, what is e to the I theta equals to, how that is being derived, and the root of unity, that is a usage of the previous result, and so on and so forth. And also maybe in the next video I would cover something in the sequence limit and something like that, hopefully. Okay, I shall stop here. That's it for this video. See you on the next video.